Wildfires pose an immense threat to ecosystems and communities across the globe. For this data science project, our team aimed to develop a robust machine learning tool to predict wildfire causes and severity. My name is Krishna, and my teammates are Josh, Jamal, and James. Our project focuses on three core objectives. The first model classifies whether or not a given fire will grow past 10 acres. This helps the authorities prioritize response time, public communication, and emergency evacuations. The second model estimates the size of a given fire. This helps determine containment strategies and resource allocation. And the third model predicts the cause of a given fire. This can help identify potential responsible parties, prevent future incidents, and improve public safety initiatives. Our project is built upon the comprehensive 1.88 million U.S. wildfires dataset from Kaggle, covering incidents from 1992 to 2015. This dataset provides rich information including fire size, discovery date, geographical location, and the reported cause. Data preprocessing was a crucial phase. We converted Julian dates to standard datetime formats and extracted the month of discovery. We also filtered data to include only wildfires within the contiguous US and handled missing values by removing columns with over 60% null entries. A big part of our work involved feature engineering. We created a binary large fire label for incidents exceeding 10 acres, numerically encoded the fire size class from A to G, and simplified the cause into a human versus natural binary flag. This correlation matrix helped us identify relationships between various numerical features, guiding our subsequent model selection. Visualizing the top fire causes clearly showed the significant impact of human activities, with categories like debris burning and lightning being predominant. Analyzing wildfires by month also revealed distinct seasonal trends, which has a noticeable increase in incidents during summer and fall months, which is important for understanding peak risk periods. Finally, mapping wildfire locations across the U.S. allowed us to observe geographical distributions and clusters, often correlating with population density and specific environmental conditions. We also created a few other visuals to help us get a better overview of our data. Our first model addresses large fire classification using random forest classifier with latitude, longitude, and month as key features. We trained a model to predict if the fire would burn over 10 acres. The model was 85% accurate, meaning it's a valuable tool for early resource allocation and strategic planning. However, one interpretation of this model is that it rarely flags large fires, indicating a bias in the model towards small fires. A way to improve the model would be to add environmental features such as temperature, humidity, wind speed, and vegetation index. For the fire size estimation, we employed a random forest regressor. To handle the skewed distribution of fire sizes, we applied a logarithmic transformation to the target variable. Features included latitude, longitude, month, fire year, and the encoded fire size class. It yielded a reasonable RMSE, indicating its effectiveness in predicting the fire area on a continuous scale. One interpretation, however, is that there is a high error, which reflects a skewed distribution and missing predictors. One important feature importance is that the month and cause often rank high, but they alone cannot determine against extreme spread potential. Finally, for our cause predictor, human-made versus natural, we utilized another random forest classifier. This model incorporated a broader set of features, including discovery day of year, owner code, state, reporting agency, which were one-hot encoded to handle their categorical nature. The model demonstrated a pretty high accuracy in differentiating human-caused fires from natural ones. One significant insight is the feature importance plot, which highlighted geographical indicators as one of the most influential factors in determining a fire's origin. It performed well for human-caused fires, but natural fires were harder to distinguish. So, what are the implications? The baseline models highlight that limited features yield poor detection of large fires despite high overall accuracy. Early warning requires richer, dynamic inputs such as weather data, fuel moisture measurements, and vegetation conditions. Comparison with other research. Our research and other research work shows that relying solely on historical patterns limits predictive insights. Research must integrate real-time climate indicators and richer environmental data sets. It must also test how these dynamic inputs improve model performance. Looking ahead, the future work could involve integrating richer external data sets such as wind, weather, humidity, drought indices, and satellite-derived fuel metrics. We could also validate against data from more recent years and perform backtesting on major fire seasons. To summarize, we built 3 models using basic wildfire record data, like time, location, and cause. First model predicted if a fire would be large, more than 10 acres. Predicted the potential size of a fire, and the third model predicted whether the fire was human caused. These models gave us a strong starting point. We saw a high overall accuracy and learned that while simple inputs catch broad patterns like seasonality and common causes, they struggle with harder tasks like spotting rare, extreme fires. Predicting the fire size or cause accurately will take more detailed data, like weather, fuel conditions, and vegetation info. To summarize, our project successfully developed and evaluated machine learning models capable of classifying large wildfires, estimating their sizes, and predicting their causes. These tools offer potential for enhancing wildfire prevention strategies, optimizing response efforts, and improving resource management.